Hi everyone! Have you ever wondered what happens when multiple threads in an operating system get stuck, unable to proceed? This is known as deadlock. In a multi-programming environment, several threads may compete for a finite number of resources, making deadlock a critical issue to understand. A thread requests resources. If the resources are not available at that time, the thread enters a waiting state. Sometimes a waiting thread can never again change state, because the resources it has requested are held by other waiting threads. Understanding deadlock is crucial for ensuring the smooth operation of systems and preventing potential system halts. System consists of resources, resource types R1, R2, and so on, CPU cycles, memory space, and I/O devices. Each resource type RI has Y instances. Each process utilizes a resource as follows: request, use, release. Deadlock can arise if four conditions hold simultaneously. Mutual exclusion: only one thread at a time can use a resource. Hold and wait: a thread holding at least one resource is waiting to acquire additional resources held by other threads. No preemption: a resource can be released only voluntarily by the thread holding it, after that thread has completed its task. Circular wait: there exists a set of waiting threads such that T0 is waiting for a resource that is held by T1, T1 is waiting for a resource that is held by T2, and so on, until Tn is waiting for a resource that is held by T0. In a real-world scenario, consider a situation where two processes are trying to access two shared resources, a printer and a scanner. Process A holds the printer and requests the scanner, while Process B holds the scanner and requests the printer. Both processes are now in a deadlock state, as neither can proceed without the other releasing the resource it holds. This situation perfectly illustrates the concept of deadlock in a practical setting. Imagine a busy office where multiple tasks need both the printer and scanner to complete their jobs. If workers are not careful in coordinating their tasks, they can easily fall into a deadlock, halting productivity and causing frustration. Understanding such real-world examples helps us grasp the significance of deadlock in computing and the necessity of designing systems that can handle or avoid these situations efficiently. By analyzing and addressing these conditions, we can create more robust and reliable software systems.